Welcome to this deep dive. We've got quite a stack of sources here looking into something that sounds, well, pretty sci-fi. Pulsar Fusion's Sunbird rocket.
Yeah, and specifically its engine, the dual direct fusion drive.
That's the one.
Our sources, they really get into the technical analysis of this Sunbird concept. I mean, what they're actually proposing here. It's definitely complex stuff, future tech.
For sure. And our mission today is really to pull out the key bits for you. We want to unpack this technology, understand why Pulsar Fusion thinks it could just completely change space travel.
Right.
And also look squarely at the massive challenges they face. We want to give you the crucial insights without you getting lost in all the technical detail.
Exactly. The big picture, minus the jargon overload.
So, Pulsar Fusion, who are they? Our sources identify them as a UK company, Aerospace, founded back in 2011. Richard Dienan.
Yep. Based in Bletchley, UK.
Which, kind of a cool historical note, Bletchley Park, the code-breaking place.
Huh. Yeah, maybe fitting for trying to crack fusion for space. Their mission statement is interesting, too. Delivering current propulsion and delivering the future through fusion.
So not just dreamers, they're doing both.
Right. They're already involved in, let's say, more conventional tech, things like Hall effect thrusters, hybrid rockets.
And they've shown they can do it, right? Like they tested a Hall thruster hitting 20 kilometers per second exhaust velocity.
Yeah, and hybrid rocket tests back in 2021. So this isn't just, drawings on a napkin. They build things.
Plus, they've invested heavily in facilities.
Yep.
2 big propulsion test chambers in the UK, maybe even Europe's biggest.
You absolutely need that kind of setup for testing advanced engines like this. It shows commitment.
Okay, so if they can build current engines, why tackle fusion? I mean, what's wrong with what we have now for space travel?
Well, it really boils down to the needs of deep space travel. Chemical rockets, great for launch, right? Massive thrust.
Get you off the ground fast.
Exactly. But their fuel efficiency, the specific impulse, or IS, it's actually quite low. So for really long trips, say Mars or beyond, you end up needing just tons and tons of fuel.
The old tyranny of the rocket equation, lifting fuel just to lift more fuel?
That's it precisely. Then you've got the other end of the spectrum, electric propulsion, ion engines.
Like Deep Space One or Dawn used.
Right. Incredibly high ISP, super fuel efficient, but the thrust is minuscule, millinewtons.
So it takes forever to get anywhere fast.
Yeah, years, decades sometimes for the outer planets, like New Horizons to Pluto. That took about a decade.
So there's this gap.
A critical gap. We need something with both high ISP for efficiency and significant thrust for speed, something current tech just doesn't offer.
And that's where Pulsar thinks fusion fits in. Their CEO, Richard Dienan, said something like, if we want to leave the solar system in a human lifetime, fusion's the way.
Yeah, it really frames the scale of ambition. It's not just tweaking things. It's a potential revolution in how we move around space.
Which brings us to Sunbird itself. Looking at the sources, this thing isn't blasting off from Earth, is it?
No, definitely not. The whole idea is that Sunbird is a reusable, they call it a migratory transfer vehicle, basically a space tug. A powerful one.
A space tug? How's that work?
Well, the concept is you use your standard rocket, a Falcon 9 or whatever, to launch your actual payload, maybe a Mars probe, into Earth orbit.
Okay.
Then the Sunbird, which is already up there, maybe waiting in orbit, comes along, rendezvous, docks with the payload.
Got it. So it lives in space.
That's the plan. And then it fires up its fusion drive, the DDFD, and gives that payload a really fast push towards its destination, Mars, Jupiter, wherever.
And once it's on its way,
The Sunbird detaches, goes back, maybe refuels, gets ready for the next job.
that actually makes a lot of sense pragmatically. You use chemical rockets for what they're good at, getting stuff to orbit.
Right, high thrust for launch.
And then you use the super efficient fusion engine for the long haul in space, where it's optimized for vacuum.
Exactly. You avoid the whole issue of trying to make a fusion engine work safely in the atmosphere or lifting that heavy engine repeatedly. Keep it optimized for space.
And you mentioned reusability, refueling. Sounds like space infrastructure.
That's the long-term vision. You'd need orbital depots, maybe refueling stations. And interestingly, Pulsar's own Hall thrusters could actually be useful for the docking part.
Okay, performance.
Oh.
This is the exciting bit. What kind of travel times are we talking about?
This is the headline promise, really. Cutting travel times dramatically. For Mars, instead of the usual 7-8 months.
Which is a long time for astronauts.
Oh, yeah. They're aiming to cut that down significantly. Maybe 3 to 4 months. The sources vary slightly. Some say under 6, some under 4, but it's roughly halving it.
And further out, Pluto.
That's even more stark. New Horizons took nearly 10 years. Pulsar's projections suggest Sunbird could get a payload there in about 4 years.
4 years instead of 10. Wow.
And maybe Saturn's moon's in around 2 years.
That completely changes the game for outer solar system exploration. Suddenly, missions seem feasible within, reasonable career spans, maybe even human lifetimes for crewed missions eventually.
It does. The speeds they're talking about are just, well, huge. Up to 329,000 miles per hour, 500,000 kph.
Some reports even mention 500,000 miles per hour with AI optimization.
Yeah, potentially even faster. That would likely make it the fastest object humans have propelled on its own, without needing gravity assists from planets.
Which is how things like Voyager got their speed boosts.
Exactly. Their models show a Sunbird pushing maybe 1,000-kilogram spacecraft, like a probe, to Pluto in that 4-year time frame.
And the reusable tug idea, how does that affect the cost side?
Potentially quite a bit. Instead of every deep space mission needing its own custom, expensive, disposable propulsion stage.
You build this reusable asset.
Right. The admittedly very high upfront cost of the fusion drive gets spread over many missions. Could lower the cost per mission, maybe lead to more regular flights, standardized interfaces for payloads.
Okay, let's dive into the engine itself. The dual direct fusion drive, DDFD. What's the physics?
Okay, so the core reaction they're using is deuterium plus helium-3, D plus He.
And that reaction produces?
It produces a helium-4 nucleus, which is an alpha particle, and a high-energy proton. So DLOL plus 3M plus He, T plus CNS, OA plus P plus He. The key thing here is those products are charged particles.
Right, and the reaction is called aneutron.
Mostly aneutron, yeah, meaning it primarily spits out charged particles, not lots of neutrons like, say, deuterium-tritium fusion, which is common in Earth-based concepts.
And fewer neutrons is good for space because...
Because neutrons are a real pain. They go through almost anything, so you need heavy shielding, and mass is always bad in space. Plus, they make materials radioactive over time.
Bad for electronics, bad for potential crews.
Definitely. Charged particles, though, you can steer them with magnetic fields. Much easier to manage, less shielding needed, lower mass.
And the direct part of direct fusion drive. That means no steam turbines.
Exactly. You're not using the fusion heat to boil water to spin a turbine to make electricity to power an ion engine. You're taking the energy of those fast-moving charged particles, the helium-4 and protons,
and using them directly.
Either channeling them out the back using magnetic fields like a nozzle to create thrust, or converting their kinetic energy directly into electrical power. Much more efficient, potentially, than going through a thermal cycle.
Richard Dinan mentioned it's a linear reactor, not like the usual tokamak donuts.
Right. It's designed as a straight tube, essentially, not trying to hold the plasma in a closed loop forever.
He said it does not need to fully constrain the plasma within.
Which sounds counterintuitive for fusion, but makes sense for propulsion. They want particles to escape out the ends.
That escaping stream is the thrust.
Precisely. They're channeling that leakage. It's a design philosophy tailored specifically for propulsion, not just net energy gain on Earth.
Okay, sounds amazing. But this fuel, deuterium helium-3, there's a catch, isn't there?
Oh yeah, a big one. Helium-3. On Earth, it is incredibly rare, and therefore incredibly expensive.
Where does it even come from?
Mostly from the radioactive decay of tritium, which itself isn't abundant. Tiny amounts exist naturally. People talk about mining it from the moon, where the solar wind has deposited it for billions of years.
But that's way off in the future. Pulsar isn't banking on lunar mining now.
No, definitely not for their current plans. So you can't just, order a big tank of helium-3 easily or cheaply.
And that impacts the engine cost.
Hugely. There was an estimate floating around of maybe $90 million for an engine, and the He-3 fuel cost would be a major driver of that price tag.
Which explains why their first tests won't actually use it.
Exactly. The initial ground tests, planned for 2024-2025, will use an inert gas, like argon maybe.
Just to simulate the plasma.
Right. To test the principles, the plasma handling, the magnetic confinement system. Can they control the superhot gas? But no actual D-He-3 fusion reactions will be happening in those tests.
They also talk about a self-sustaining fuel supply. What does that mean? Breeding fuel.
That's the implication. Inside the plasma, you can get side reactions like deuterium fusing with deuterium. That can produce some tritium, which then decays into helium-3.
So the idea is to capture that internally produced He-3.
Yeah, essentially breeding some of your own fuel to reduce the need for external supply. But Pulsar hasn't really published details on how their specific linear design would achieve this efficiently enough to make a difference. It's a complex process.
So bottom line, the whole economic case for Sunbird seems to really depend on finding cheap P3 somewhere or proving this breeding cycle works really well.
It's absolutely critical for this to be more than just a, fantastically expensive science experiment. It needs a viable fuel cycle.
Let's get back to the engine design and numbers. Linear reactor.
Right, a straight chamber, inject plasma, pulse magnetic fields to accelerate and collide the streams, hope you get fusion.
And the controlled leak out the back is the thrust.
Yep. Using the escaping plasma, not fighting to contain it perfectly forever like terrestrial fusion aims for.
But containing plasma at hundreds of millions of degrees, still incredibly hard.
Oh, absolutely. It's one of the toughest physics challenges there is. Plasma behaves almost like a chaotic weather system. Pulsar mentions proprietary technology here, a closely guarded secret.
So we don't know how well it works yet.
Not publicly, no. Its effectiveness is unproven outside their labs and simulations.
Which is why the simulation work with Princeton satellite systems is so important, using AI.
Crucial. They've been working together since 2023. Modeling this plasma chaos with supercomputers and AI is how you gain understanding and hopefully optimize the design before building very expensive prototypes.
Okay, so based on those models, what are the performance numbers they're aiming for? Specific impulse.
They're projecting ISP between 10,000 and 15,000 seconds.
Which, compared to other engines?
It's huge. Chemical rockets, maybe 450s. Nuclear thermal propulsion, NTP, maybe 800 950s. Good electric thrusters, maybe 1,500 to 5,000s.
So 10,000 plus is just way, way more efficient.
Dramatically more fuel efficient than anything really on the table right now.
Okay, what about thrust? How hard does it push?
For the 2-megawatt version they often discuss, the thrust is projected in the range of 10 to 100 newtons.
Which is about 2.25 to 22.5 pounds of force?
Correct.
That sounds kind of low compared to a chemical rocket launch engine.
Very low compared to a launch engine, yes. Those need millions of newtons to beat gravity. But compared to electric propulsion, which is often fractions of a newton,
it's much, much higher.
Orders of magnitude higher. So it's in this interesting middle ground. Extremely high efficiency, like electric, but with moderate thrust. Much more than electric, though less than chemical or NTP.
So it's not an instant kick, but a steady, efficient push that builds up speed over time in space.
Exactly the idea. Perfect for that space tug roll, accelerating payloads gradually but very efficiently. There was one mention of a much higher thrust, like 1,000,000 pounds, but that seems to relate to maybe much larger future concepts, not the current Sunbird plan. The consistent numbers are in the tens of newtons.
And the dual capability makes power too, up to 2 megawatts.
Yes, and that's a really big deal. 2 megawatts of electricity is enormous for a spacecraft. The ISS, with all its solar panels, generates about 120 kilowatts.
So what does that kind of power enable for you thinking about future missions?
Well, it means you can run much more sophisticated, power-hungry science instruments. You can have much higher bandwidth communications back to Earth, crucially when you get far from the sun where solar power is weak.
Like Jupiter or Saturn or beyond.
Exactly.
Yeah.
That 2 milliW could power surface operations, maybe early resource extraction, life support for potential future crewed missions. It fundamentally enhances what you can do once you arrive, beyond just getting there faster.
So the DDFD aims for this unique sweet spot then?
Yeah, if you look at the comparisons, it's trying to bridge the gap. High ISP, like electric, but with thrust levels way beyond typical electric drives. A new category, really.
Okay, great theory.
Huh.
But how do they plan to actually build it? What's the roadmap look like?
Well, they say they've been working on it quietly for about 10 years, which lines up with the company's founding. They're now in phase 3, actually manufacturing the first test article. The big public reveal was around March 2025.
And the ground tests are starting soon.
Planned for 2024 and 2025. But remember, these are using inert gas, not the actual DHE3 fuel.
Right, testing the plasma handling the confinement,
Yeah.
but not actual fusion.
Exactly. Using their Bletchley vacuum chambers to validate the basic operations.
And the AI modeling work with Princeton continues in parallel.
Yes, that's ongoing and vital for refining the design and understanding the incredibly complex plasma behavior before they get too far with hardware.
Then things get really ambitious with the space tests, the IODs.
Yeah, there's talk of some component tests in space late 2025, maybe testing the power supply or some electronics.
But the big one everyone's watching is 2027.
Right. The target is 2027 for a key in orbit demonstration. The goal stated is to achieve fusion in space. Other descriptions say a small-scale linear fusion experiment to validate underlying physics.
Okay, achieving fusion in space by 2027. Given that ground tests won't even use fusion fuel,
Yeah.
that sounds, well, extremely fast.
It is undeniably very ambitious, high risk. Fusion research has taken decades on Earth. To go from inert gas ground tests to demonstrating DHE-3 fusion, even small scale, in orbit in just 2 or 3 years, that's a monumental jump.
The complexity of building, launching, operating that in space.
It's immense. What exactly they mean by achieve fusion or validate physics in that 2027 test will be really important. How much fusion? For how long? Under what conditions? The details matter hugely.
Assuming they do hit that 2027 milestone, when might we see an operational Sunbird?
The timeline suggested points to the early 2030s, maybe around 2032, if the 2027 test is successful and development continues smoothly.
But even the CEO admits that's speculative.
Yes, Richard Damon himself called a full prototype timeline too speculative, which is a realistic acknowledgement of the huge uncertainties involved here.
They also plan to release some linear fusion-based models in 2025. What's that about?
Likely theoretical work, simulation results, maybe data from smaller lab experiments. Releasing that kind of information helps engage the wider scientific community.
Get feedback validation.
Exactly. And build confidence, which is crucial for attracting the significant investment needed for the later, much more expensive stages.
Okay, so the exciting vision, the ambitious plan. Let's circle back to the challenges. We know about helium-3, but what else makes this so incredibly difficult?
Look, it's a massive undertaking. Fusion is hard. Space is hard. Combining them, well, it multiplies the difficulty.
The helium-3 issue just doesn't go away, does it?
Not yet. The scarcity, the cost, the lack of a clear, detailed public plan from Pulsar for either a cheap source or a proven self-sustaining breeding cycle, it hangs over the whole project's long-term practicality.
And the core engineering challenges. Beyond fuel.
Controlling the plasma. That's number one. Getting that super hot, chaotic plasma stable inside their linear machine, using their proprietary magnetic confinement. Proving that works reliably is the absolute make or break technical step.
Then you got the materials. What holds this thing together?
Critical question. Components near the plasma face intense heat, particle bombardment, some residual radiation. They need materials that can survive that for years in space while being lightweight. That's a huge materials science challenge.
And Dr. Lozano at MIT mentioned the difficulty, especially in compact devices.
Right. Making fusion work is hard enough. Making it work in something small and light enough for a spacecraft adds another layer of extreme difficulty.
Plus, you have to reliably ignite the fusion, keep it going as needed for thrust and power.
Even if it's pulsed, yeah.
Yeah.
And efficiently channel those energetic particles out the back without the plasma becoming unstable or damaging the engine. These are fundamental problems.
So what's the view from outside experts? Cautious.
Generally, yes. Dr. Lozano, for instance, expressed skepticism about near-term feasibility in compact systems without seeing the specifics, suggesting maybe 10-plus years for a prototype. He even referenced the old joke.
Fusion is always 20 years away.
That's the one. But there are nuances. Dr. Aaron Knoll at Imperial College suggested maybe fusion for propulsion doesn't face all the same hurdles as fusion for grid power.
Implying the requirements might be slightly different, possibly achievable sooner.
Potentially. It's an interesting perspective. Maybe space propulsion is a slightly less demanding application in some ways.
Pulsar themselves argue space makes it easier in some respects. The vacuum, the cold.
That's their argument. Space provides a perfect vacuum, so no need for giant pumps like on Earth. The extreme cold helps with managing heat and potentially with superconducting magnets, and their linear design is naturally suited to exhausting particles for thrust.
But space brings its own nightmares.
Oh, absolutely. Extreme reliability is paramount. You can't send out a mechanic. Everything has to survive launch, vibrations, radiation. And testing, iterating, fixing things in orbit is incredibly expensive and complex compared to a lab on Earth.
So theoretical advantages meet harsh practical realities.
Pretty much. Success really boils down to, does their secret confinement tech work as claimed? And do they have a real answer for helium-3? They're tackling the core fusion challenges plus the unique difficulties of spaceflight.
Are they getting any help? Partnerships? Government support?
They have key partners. That Princeton Satellite Systems collaboration for the AI and supercomputer modeling is vital. Gives them insights they couldn't get otherwise.
And government funding, UKSA.
Yes. They have received UK government and UK Space Agency grants. Interestingly, one specific UKSA grant mentioned focuses on fission-based propulsion.
Fission, not fusion, so a different nuclear path.
Right, they're pursuing that too, with partners like the Nuclear AMRC and Cambridge University. It shows government confidence in Pulsar's nuclear space capabilities generally, and maybe provides some R&D diversification.
Could there be overlap? Lessons learned.
Definitely potential synergies. Things like materials science, safety protocols, systems engineering for nuclear systems in space, those lessons could apply to both fission and fusion efforts. Fission might even be seen as an interim step.
And they're protecting their ideas. Patents.
Richard Dinan holds patents, yeah, though the specifics aren't detailed in our sources regarding the DDFD. They definitely emphasize the novelty of the Sunbird DDFD concept and are keeping key aspects, like the confinement tech, closely guarded, protecting their intellectual property.
Okay, let's pull this all together. Sunbird, hugely ambitious. If, and it's a big if, they pull it off, what's the ultimate impact?
It's transformative. Simple as that. Cutting travel times like that, Mars in months, outer planets in a few years, it just rewrites the map for space exploration. Makes missions possible that we can barely even dream of now.
And don't forget the power aspect, that 2 megawatts.
Crucial. Because you need to think beyond just getting there fast. What can you do when you arrive? That power enables complex science, high-speed data return, maybe supporting habitats using local resources, especially vital far from the sun. It unlocks vastly more capable missions.
But we have to keep saying it. High risk, high reward.
Extremely. The fundamental challenges are still there. Controlling the fusion plasma reliably. And solving that helium-3 fuel problem. Those are the big mountains to climb.
So the next few years are absolutely critical to watch.
For sure. Those inert gas ground tests are the immediate next step. But the real focus will be on that 2027 in-orbit demonstration. What does it achieve? How well does it work? That will tell us a lot.
And even if the full Sunbird doesn't happen exactly as planned, is the effort still worthwhile?
Oh, absolutely. Just tackling these problems pushes the boundaries across so many fields. Plasma physics, materials, power systems, direct energy conversion, complex simulations, the knowledge gained, the technologies developed along the way. That has value regardless of the final outcome for Sunbird itself. It moves the whole field forward.
It really is an incredible project to follow. Okay, final thought for you, the listener. Considering everything, the physics challenges, the engineering hurdles, especially that helium-3 supply issue and mastering the plasma, what do you think is the single biggest breakthrough pulsar fusion absolutely must achieve in the next few years to keep the Sunbird dream alive and credible? Definitely something to ponder.